Hello and welcome to another edition of Ontology Talk. Today we have a guest lecture on the topic of neighborhood semantics, an approach to possible worlds reasoning that's appropriate for some of SUMO's higher order predicates.
In this video, we'll be giving a quick and informal introduction to the way neighborhood semantics with possible worlds can be used to interpret the knows predicate in SUMO. In logics like high-order logic, for example, you'll have propositions, and these propositions are intended to be true or false. A common example in mathematics is a statement like 2 plus 2 equals 4, which is true, versus 2 plus 2 equals 5, which is false. So if you had a model, you would expect in that model that the interpretation of 2 plus 2 equals 4 is true, but the interpretation of 2 plus 2 equals 5 is false. But if we pass from the world of mathematics to the real world, or common sense reasoning, it's more complicated, of course. A very well-known example in quantum mechanics is Schrodinger's cat. Here we can simplify things a bit and simply say there's a cat in a box and it's either alive or dead, and we don't know which until we open the box. So let's say there's a proposition D, meaning the cat is dead. Now if you gave some kind of interpretation, let's say I would be interpreting the cat to be a particular cat, and would interpret dead, presumably to mean, true if the thing is dead. And so D would be true in that interpretation I, if and only if the cat is actually dead. Or, to be more precise, the cat is dead in the interpretation I. Likewise, in a different interpretation I, the I may not model the D. Not modeling D is the same as modeling not D, the negation of D, meaning the cat is not dead. And all this is relative to the interpretation. I'll say in I. Let me give these different names now. You've got two different interpretations, one in which the cat is dead, one in which the cat is not dead. In each interpretation, it's going to be one or the other. But in common sense reasoning, like in SUMO, there are also these knows predicates. So you can say, knows Mary some proposition. So now let's fill in the proposition with D. We'll say, knows Mary D. This means Mary knows the cat is dead. Now let's make a few basic assumptions about this knows predicate. First, let's assume that there's a true proposition and a false proposition, and that in every interpretation the true proposition will hold and the false proposition will not. Now furthermore, let's assume that every agent A knows true and every agent A does not know false. Next, let's assume that if two propositions B and C are equivalent, then an agent A knows B if and only if A knows C. Finally, let's assume that if an agent A knows B and an agent A knows C, then the agent A knows B and C, the conjunction of B and C. Under these conditions, it's easy to see that the knows predicate becomes trivial in an interpretation like I1 or I2. Why is that? Because in I1, the cat is actually dead, so the proposition D is equivalent to true. Mary knows true, so Mary knows D. In the interpretation I2, the cat is not dead, so that not D is equivalent to true in the interpretation I2, so it necessarily follows that Mary knows the cat is not dead in interpretation I2. In general, for any agent in any interpretation like I1 or I2, where a proposition is just given a truth value, the agent will know a proposition P if and only if that proposition P holds in the interpretation. So this makes the knows predicate trivial and certainly not what we intend by the knows predicate. it's more realistic to say, well, if Mary has not opened the box, then Mary does not know D and does not know not D. She knows neither. So you want to have some kind of interpretation. I'll just say I3, in which Mary doesn't know D, but Mary also doesn't know not D. She knows neither. Now, this wouldn't work with I1 or I2 because in the case of I1, if she knows true things, she'll know D. In the case of I2, if she knows true things, she'll know not D. And you can't distinguish between things being true and her knowing them. A common way to deal with these kind of issues in modal logic is to have a kind of possible world semantics. So instead of simply saying that a proposition is true or false in the interpretation, you have a set of worlds, and it's true or false in a world. So let's say I3 has a notion of worlds. So let's say W is a set of worlds. And I'll use little w's to range over the w's. I'll write this notation to mean the proposition P is true in W in the interpretation I3. So this means there is a set of worlds, W, where D is true, and there's also a set of worlds, W, where not D is true. This is the same as saying D is not true in the world. Let's give these two sets names. I'll call the first one X. Those are the worlds where it's dead. I'll call the other one Y. Those are the worlds where the cat is not dead. Now, we can't have it being both dead and not dead. So when you intersect these two sets, you get the empty set. And likewise, it has to be one or the other in each world. So when you union them, you get the set of all worlds. Now we have a set W of worlds. We have X being the set of all worlds where the cat is dead. And we have a set Y, the set of all worlds where the cat is not dead. And we know X union Y is all worlds, and X intersect Y is empty. Now, how do we model Mary knowing? What does it mean to say, in a world W, knows, I'm using this prefix notation because SUMO uses it, Mary D. And what does it mean to say, in a world W, knows Mary not D? Well, we can be a bit informal here and just replace this D with its X. So now we're thinking of the meaning of the proposition as being the set of all worlds where that proposition is true. And likewise, we'll say Y here. In order to know if W makes knows Mary X true or knows Mary Y true, we'll use something called neighborhood semantics. So we'll assume there's some function n that goes from worlds to the power set of the power set of worlds. And now essentially, knows Mary will correspond to some function n like this. And if we want to know if W makes knows Mary, I'll say Z, where this is some set of worlds, so in the power set of worlds, then we just ask, is Z a member of NW? This is for the n that corresponds to knows Mary. And now we'll see it's possible for Mary to know neither of them. So let's let X prime be the set of all W such that in that world, W knows Mary D. And Y prime will be similar. It's the set of all worlds where knows Mary not D. Now that we're including possible worlds in our semantics, it makes sense to relax the condition that knows is closed under equivalence. Recall that we said if two propositions B and C are equivalent, then an agent A knows B if and only if A knows C. We'll continue to have this condition, but now we'll quantify over the worlds and the hypothesis. So we'll only require knows to preserve this equivalence if B and C are equivalent in all worlds. Note that propositions like D and not D are not equivalent to true or false anymore because they're only true in some worlds, whereas true is true in all worlds. So X prime are the worlds where Mary knows the cat is dead. Y prime is the set of all worlds where Mary knows the cat is not dead. Intuitively, this means when you union these two, it's the set of all worlds where Mary has opened the box to look and see is the cat dead or the cat not dead. That doesn't need to be all worlds. So it's certainly a subset of worlds, as you would expect. Every proposition will be interpreted as a set of worlds now, but it doesn't have to be all worlds. So in a very simple case, you could say there's three worlds. I'll call it W0, W1, W2. And you could have Mary knows that the cat is dead in world 1. Mary knows the cat is not dead in world 2. And Mary doesn't know either in world 0. W0 is either a member of X or W0 is a member of Y. But that doesn't mean that W0 has to be a member of X prime or Y prime. So, in fact, I can say, I can choose the worlds and the interpretation so that W0 is neither, even though W1 is in X prime, W2 is in Y prime. It's natural to ask if X prime intersect Y prime has to be empty. In fact, we can conclude that no world can be in both X prime and Y prime using the assumptions we gave earlier about the knows predicate. If Mary knew D and Mary knew not D, then Mary would know the conjunction D and not D. But D and not D is equivalent to false, so Mary would know false. That's contrary to our assumption earlier that no agent knows false.
Thanks for watching today's guest lecture. I hope you've found it enjoyable and useful. If you have, please consider liking and subscribing to our channel. Thanks very much.